So this was the explanation about the watchdog timer and all the other details. So now again we can have the application or the explanation about the ATM timer, right? And most of the things have been discussed before. This 2 millisecond was the range of the scale register, right, which was the resolution of the time register. You multiply it by 2 raised to power 16, it comes out to be 131070 millisecond, which is the maximum count that this ATM timer can count. But we have to initialize for 2 minutes, which is 2 into 60 into 1000. So now the time register value is 131070 minus this 120,000, which comes out to be 11070. So if we initialize the time register with this value, when the time register would overflow, exactly 2 minutes would have passed. So this is the idea. Another watchdog timer application is in the mobile phone, and in this application display is off. In the case no GUI interaction takes place within a watch time interval, right? So we can set the display to go to blank after 15 seconds, 20 seconds, 25 seconds or 30 seconds if there is no activity on the touch screen, right? So this saves power. Just visualize how important the watchdog timer is for the different kinds of applications. Okay, there can be more applications. Another application is temperature controller. Is that if the controller takes no action to switch off the current within preset watched time interval, the current is switched off and a warning signal is raised, indication of controller failure. Failure to switch off current may burst a boiler in which water is heated. Again, a safety measure. Let's say we are turning on the current in a boiler, so we also start a watchdog timer, and the watchdog timer would overflow. Let's say if we want the current to be on only for 2 minutes, we set the watchdog timer to overflow in 2 minutes, after which the service routine would be called to switch off the current to the boiler. If we basically fail to switch off the current in our code, the watchdog timer would kick in after the 2 minutes timeout, and it would switch off the current. So it's basically a safety measure that we can have. Okay, some points about provisioning of the watchdog timer. Watchdog timer can be hardware based, like I discussed before, in which it is a separate hardware running on its own oscillator, hence the term free running timer. Or it can also be a software task that is programmed as a watchdog timer. This software task would be acting as a watchdog timer. It would execute in the background, and let's say after a preset time interval it would generate an interrupt, and when the interrupt is generated, the code would be transferred to the ISR or the interrupt service routine that executes the tasks that are involved when the watchdog timer is overflowing. So what is the disadvantage of having this software based watchdog timer, right? Number one, it is more power consuming because you are executing instructions, right, to act as a timer or to act as a watchdog timer. And point number two, if some code execution failure occurs that hangs your system, the watchdog timer is supposed to be hung as well. So in low cost microcontrollers which might not be having a watchdog timer, this is the approach that would be taken. Now we look at serial transmission using UARTS, universal asynchronous receiver and transmitters, right? Basically, serial transmission consists of two types. You can have a UART, universal asynchronous receiver transmitter, which only transmits in the asynchronous mode or mode without the clock, whereas we can also have a USART, which is universal synchronous asynchronous receiver and transmitter. So USART has got both the options of synchronous clock-based communication as well as asynchronous non-clock based communication. So UART, universal asynchronous receiver transmitter, it takes data parallel and transmits it serially. Basically, transmission of UART is similar to the parallel to serial conversion in the registers, like we discussed in digital logic design, right? We have got a parallel register and we shift out the bits from the parallel register one bit at a time serially on the transmission line. On the other hand, we'll have serial interface, which is connected to the receiver line on RX, and over here we have serial to parallel conversion. Each of the bits is received serially by the receiver, and in the end they are converted into 8 bits. So this is the idea. Now we can have the parity bit as well. Parity is basically extra bit for error correction or error checking, right? And we can have the start bit and stop bit. Basically what happens is that whenever we are transmitting data using the synchronous mode or the clock based mode, the clock is enough to synchronize all the data transfer, right? You know that flip-flops can change either by a positive edge or a negative edge. So when we are discussing those kinds of arrangements, which are synchronous arrangements, we are also having a clock signal over here. So since we are having a clock signal over here, there is no need for any start and stop bits in that thing, because everything is synchronized with the clock. But on the other hand, if we have the asynchronous mode, in asynchronous mode there is no clock signal that is transmitted. So when that no signal is transmitted for the clock, we must synchronize the transmission and reception by using the concept of the start bit, a single bit that indicates that the transmission is starting from the transmitter side, and a single bit that indicates the end of the transmission from the transmitter side. So what does the transmitter do in asynchronous mode? It first transmits the start bit, which is a signal to the receiver to get alert because the transmitter is transmitting the data. Then the data bits are transmitted after the start bit, and to complete the frame, the end bit is transmitted. There can also be parity bits, which are used basically for error checking, right? And the start bit can be one single 1 bit time, it can be 1.5 bit time, or it can be 2 bits time. And as I discussed before, in modern approaches we don't have the classical serial ports, so we can have this FTDI chip, FTDI232BL chip based device, that is basically a bridge between the USB and the UART. So your microcontroller can connect to the UART portion over here, and the communication from the UART is automatically transmitted to USB and sent to the PC. So the advantage is that your device can communicate with the USB of a host system or a personal computer without any added complexity of the USB protocol. As the USB protocol is very difficult to implement, it is handled automatically by this chip, and this chip can be configured on the Windows environment by using the VCP or the virtual COM port drivers. Okay, so it's called a VCP bridge or virtual COM port bridge as it is called. And we also discussed basically what would be the bit time. Bit time would be 1 over the baud rate, where baud rate is the signal changes per second. So if we are given a baud rate, the inverse of the baud rate would give us the bit time. One important thing is that, a very important point is that when the transmitter and the receiver are transmitting and receiving using a UART, the baud rate for both the transmitter and receiver must be the same. The number of data bits transmitted must be the same. The number of start bits setting must be the same for both, and the number of stop and bit settings must be the same for transmitter and receiver. So that's a very important point. So you can't have the transmitter running at 9600 baud and the receiver running at 4800 baud. It won't work. You will get garbled data. Or you can't have the transmitter having one stop bit and the receiver set for 2 stop bits. Again, you will have garbled data or confusing data, right? Incorrect data. So now let's look at about UART. You can read this slide down. What does this say? UARTs are not available as classical UARTs, right? With those DB9 and DB25 connectors like these. But UARTs are available as virtual UARTs, like I discussed before, right? Using the FTDI chips, which converts from the UART to the USB and from the USB to the UART, and is handled by VCP drivers for the operating system. So this is one of the arrangement that has been shown, right? The data bus can transmit data parallelly to the UART1, and UART can transmit serially. The TX line connected to the RX and the TX over here connected to the RX over here. It is received by this is the transmitter UART, this is the receiver UART, and the receiver UART converts the serial bits to parallel data bus that can be accessed by the receiver. So this is basically TX and this is basically the RX. Now in classical UARTs, when we had those COM ports, right, we had to shift the level of the TX and the RX signal from 0 and 0.5 volts to the levels for the serial communication RS232 or RS485. So these max 232s would shift the level of the signal. So they were called level shifters. So TX signal level would be shifted to the new level to be transmitted by the wire. And on the receiver side, the max 232 would convert the shifted signal back to the TTL level signals for the UART2 to understand. So this was the idea, right? Now of course we would since we would be using the USB, so this max 232 would be necessary. The FTDI can be placed over here, and the FTDI would convert, but basically I think yes, this would be the FTDI now instead of the UART, which would contain the serial protocol followed by the USB protocol. Now how this scenario would change, it would be made more clear by a diagram, right? So this is basically our embedded system, right? And the TX and RX lines are connected to FTDI chip, and the data would be transmitted, and again it would be handled by the FTDI chip, TDI, and this is basically USB, right? And basically this FTDI can be connected to the PC, this refers to a solution where the PC is also using the FTDI chip for protocol conversion. There can be other thing that it might not be using FTDI, it might be using a dedicated USB controller. Whatever is the case, a block would be over here to handle the USB, and the USB protocols and data can be converted to RX signal over here and TX signal over here, right, for data communication. So this is our basic idea. So where will you find the UART, right? You'll find the UARTs in any DIY electronics projects, right? That might connect GPS modules, Bluetooth modules, RFID card reader modules, whatever, right? So basically anything that connects to your embedded system externally, see here, so any peripheral or any device, it might be card reader. So any device that connects to your embedded system would connect through the UART. In fact, Cisco provides different kinds of routers, right? And routers also contain this console port, which is basically a UART port. Now these days the USB ports have been replaced by the UART ports, but the idea is still the same. So UART can be a physical circuit built into the microcontroller as a peripheral, or it can be a standalone IC, right? And a standalone IC is one example like this that we saw before, UART1 and UART2. So what is the main function of UART? It's to transmit and receive serial data. And as I've discussed before, routers can be controlled via console port, and peripherals would be designed as IO modules. This is one thing that we can understand. And we have discussed the concept of the IO modules before. They contain data registers for input-output of data, they contain control registers for configuration, and they contain the status register for finding the status of the module. So what is the best thing about the UART? It requires only 2 wires to transmit data between the devices. And for that matter, USB is also a serial protocol, so it requires only 2 wires, data plus and data minus. UART communication, 2 UARTs communicate directly with each other. The transmitting UART converts parallel from a controlling device like CPU to serial form, and transmitted serial to the receiving UART, which then convert the serial data back into the parallel data for the receiving device. Like I have discussed before, this is similar. This is one point that we discussed before. So UARTs can transmit data asynchronously, which means there is no clock signal to synchronize the output of bits. Instead of a clock signal, the transmitting UART adds start and stop bits to the data packet being transferred. These bits define the beginning and end of the data packet, so the receiving UART knows when to start reading the bits. So all synchronization is done by using the start and the stop bits, right? And we can also have a parity bit, right? And what is the concept of the parity bit? We have the transmitter and we have the receiver. Let's say transmitter transmits 0 0 1 1, right? So there are 2 ones, so transmitter's parity is even. So the transmitter calculates this parity bit, which is even because we have 2 ones, which is an even number. It transmits the data along with the parity bit to the receiver. For example, if the receiver receives this data 0 0 1 0, so receiver receives the data, it calculates its own parity. Now the calculated parity is odd because there is only 1 1, right? So now the received parity is even, but the calculated parity is odd, so it means an error in transmission. So the receiver can request the transmitter to transmit the data again. So what is the main limitation of parity? Parity can only detect a single bit in error. So for example, if the receiver receives 1010, the data is wrong, but the parity bit would be calculated over here to be even, and the parity bits would match. So parity won't be able to catch these kinds of errors. So some parameters for UART communication, right? These are the parameters that must be configured, right? The wires used would be 2. This is the baud rate. This must be the same for both the transmitter and the receiver, and it can be up to 115200. Usually for noisy environments we keep it low, like 9600 watts. Which mode? If it is a USART, you can configure either the synchronous mode or an asynchronous mode, right? Serial or parallel, it is serial, right? Maximum number of masters 1, maximum number of slaves 1, right? This is true for RS-232. But when we are communicating with the other standard, which is RS-485, the number of devices might be more than 1, or more than 1 transmitter, or more than 1 receiver, or in total the number of communicating devices may be more than 2 in the case of RS-485. So some points about the baud rate, right? When the receiving UART detects a start bit, it starts to read the incoming bits at a specified frequency. So the receiver's frequency is basically the frequency at which the receiver is reading, and this is called as the baud rate. So baud rate is a measure of the speed of data transfer. It is expressed in bits per second. So what is the main condition? Both UARTs must operate at the same baud rate. The baud rate margin between the transmitter and the UART can only be at about 10% at most. If it is, the difference is more than 10% between the baud rate of the transmitter and the baud rate of the receiver, then the timing would get bad and will have bad results, or garbled or garbage data. So how does it work? In a UART or asynchronous mode, data is transferred in a packet form. A packet has got a one start bit, and the data bits can be 5 to 9 bits. The parity bit is optional. The transmitter can be programmed to send the parity bit, and the transmitter can be programmed not to send the parity bit. And then we have 1 to 2 stop bits. So this is the complete packet. So what is the start bit? The UART data transmission line is normally held at a high voltage level when it is not transmitting data. To start the transmit data, the UART pulls the transmission line from high to low for 1 clock cycle. Now this is the start bit when the data line drops from high level to low voltage level. So then the receiver would start to read the bits at the frequency of the baud rate. So data frame consists of a number of bits which can be from 5 up to 8 bits. If no parity bit is used, right, the data frame can be total of 9 bits. And what is the scheme? The least significant bit of LSB is transmitted first. Parity bit, and parity bit that we have described, it defines the evenness or the oddness of a number, right? And we can simply use it for detecting the better how the number of ones. If even number of ones is transmitted, the parity is even. If odd number of bits is transmitted, the parity is odd. And we have already discussed how this parity bit can be used. And this is again the demo, right? So this is basically how the thing can be done, right? So if we have a certain scheme of even and odd, we can have this. If the parity bit is 0, we can have it signifying even parity. So parity bit would be 0 if we have the even number of ones, and it would be 1 if we have odd number of ones. So in adding to the previous example, the transmitter is sending this pattern. So again, the number of 1 is 1, which is an odd number. So parity bit is 1. It is received by the receiver, right, and the receiver receives this pattern and the calculated parity by the transmitter, which is 1. But now the received data pattern is even, so the calculated parity now is 0. Since these parities don't match, it means an error and the data must be retransmitted. But again, if we have this kind of thing, right, which is more than 1 bit in error, 2 bits in error, right, these 2 bits are in error. So now again the transmitted parity was 1 and the calculated parity P dash is again 1. So the receiver won't be recognizing that this is an error. So parity can only detect a single bit in error.